Hi there, this episode is an audio rip of a YouTube video. If there are any references to the screen or to the video itself, then be sure to go over to YouTube and actually check out the video, which will be the same title as this podcast. Thanks. Hello there and welcome back to the 18th edition series. Now, today we're going to take our look at the second chapter of part 4. So the previous video was protection against electric shock, where we talked about automatic disconnection of supply. We talked about class 2 self-pelf and electrical separation as the common protective measures. There were some specialist scenarios where you'd obviously have an electrical installation under skilled or instructed use, but that's the first part of part 4, is the under protection for safety. Now, moving on, we're going to talk about now chapter 42. Now, this is protection against thermal effects. Now, this is still a fundamental principle. Actually, it's covered in 131.3 back in part 1. So we know that thermal effects must be considered in the design phase of an electrical installation. Thermal effects is it's a easy term to throw around without actually really thinking about what we're trying to talk about there. So we need to understand the potential of arcing, we need to understand the potential of load temperatures, the potential of the environment the installations can be built in, and also just surface temperatures under normal use. So there are a number of things we must consider with regards to thermal effects. It's not a consideration really of an increased temperature during a full condition. We're going to cover that later on. It's more the general operating characteristics. Whilst electricity is a source of energy, as it is used, energy is lost through quite often thermal losses. So we always need to make sure we understand what these losses are, and we need to make sure that we enable the building and the persons to be protected against this risk. A good example of that I had with one of my clients was here. This was a simple. I say simple. Here's the lead coming in that actually belonged to the site, which was from their supply, and this is the fixed plug underneath a refrigeration unit for a large trailer. Obviously they run on diesel, they come in, but they actually have to switch over to plug power whilst they're idle and being loaded up. And after a sustained period of time, this excessive temperature occurred, and clearly, whether you conclude this to be a loose connection fault or an overload fault, I've recommended further investigation to the cabling with regards to that. It's probably a loose connection issue. But you can see a sustained overload has created a detrimental effect, and these could always have it could be a real catastrophe if there's a fire scenario after this. Now we see this a lot with simple domestics with regards to the luminaires and the connections on the luminaires, and again, that's why we did mention in the previous video about the need for RCTs now to be on circuits for luminaires in dwellings. That also will help with regards to protection against fire there as well. But looking into this, chapter 42, we've got: you need to consider the harmful effects of heat or thermal radiation developed by electrical equipment. So, in normal use, or maybe in a fault scenario. The ignition, combustion, or degradation of material. It's always, it's important to remember that we did suggest in part 1 that equipment shall be selected to ensure its life will not diminish. If electrical equipment is installed or used in such a way that the life isn't, that it's not suitable, its life will start to diminish. And if the equipment's life diminishes, one of the first signs of evidence of this is breakdown in insulation, or the development of arcing due to damaged or weakened or brushes, etc. in the contacts. When things break down, they start to scream for attention. Quite often, arcing or thermal events occur as one of the potential obvious signs of that. We're going to look at flames and smoke, where a fire hazard could be propagated from an electrical installation to other nearby fire compartments. So we also have to consider compartmentalization, understand how the building is going to work with regards to handling a fire. And it's going to obviously, there are issues with regards to compartmentation, there are issues with regards to smoke travelling within a building. We've got to make sure that all that's considered with as well. And safety service being cut off by failure of the electrical equipment, so we need to make sure that if any of the electrical equipment does fail due to a thermal effect, such as a fire, that a safety service is not disconnected. So if you think about emergency lighting, that's a safety service. But most times these days, especially in small scale shops and pubs, a lot of the emergency lighting will be maintained or self-contained within the luminaire. That's absolutely fine because there's not a wiring system. There's no wiring system for that emergency lighting. All of it's self-contained in the luminaire. It's got its own transformer, its own battery source. But if instead we had a battery bank or a standby diesel-driven generator, that lighting distribution system, which you'll see that kind of system in some older buildings. I see it a lot in sports halls, sports centres, even some sheltered housing. You may get some very low wattage lights over the doors, etc. But that wiring system has to be installed in a way that its life won't diminish, and we have to consider that right now with regards to the potential thermal effects that can occur to safety services. So we must make sure that they're not being cut off if there's a failure in any equipment as a consequence. Right. We are going to cover that later on anyway with safety services, so it's not a problem at this point. We see evidence of overheating, overload. Very common examples, especially in domestics or in some offices where there's insufficient points of utilization, insufficient sockets. We'll see the plug adapter. You may see these. If these are unfused, they have to be replaced. But if they are fused, you still need to make sure that there's not excessive loading on them. It is a requirement of the IET's Code of Practice for the service inspection and testing of electrical equipment, which is the PAT tester's book. One of the things the PAT tester is supposed to do on his rounds is to identify how many points of utilization there are. So if they go to a room and they find 20 to 30 items, and those items belong to that room, and it's obvious that those items kind of work together. They're not one or the other. They all work at the same time. If he only counts 10 or so sockets, then clearly there's going to be extension leads. That's not acceptable. An employer must ensure that the fixed wiring is adequate for the demand of the employee, and that it then has effective maintenance. An extension lead or an adapter like this is not acceptable. You've got an insufficient fixed wiring system. So anytime that you see, stuff like this should not be designed, stuff like this should not be intended, stuff like this should be remedied and worked around, because we get this a lot. We get this kind of thing happening a lot now. Okay, so that talks about that 421 causes of that. Now 421.1.3. Remember I mentioned about maybe putting these up if they're quite popular. This is where arcs, sparks or particles at high temperature could be emitted by the equipment in normal service. This is fixed equipment. In normal service, the equipment shall meet one or more of the following. So it will be totally enclosed in an arc-resistant material, meaning the arc and particles can't escape. So the surrounding environment is safe. Screened by resistant material from materials upon which the emissions could have harmful effects. So there's, you've got a material that's combustible and you've got arcs, but between those two materials you've got a screening that stops one area affecting the other. Mounted so as to allow safe extinction of the emissions at sufficient distance from these materials, so they're mounted at a distance from combustible materials, or in compliance with the product standard that accommodates this practice. And then we have .1.4. Fixed equipment causing a concentration or a focusing of heat shall be at a sufficient distance from any fixed object or building element, so the object or element is not subjected to a dangerous temperature in normal conditions. Luminaires is a good example of that, which we'll cover separately in a minute, because they concentrate heat as part of their design. But any equipment that creates a focal heat point We need to make sure that wherever that hot point reaches, there's no combustible materials or combustible structures. To be perfectly honest, if you follow the manufacturer's instructions, they should have identified a temperature from combustible material and it should be in there. But again, it could be that you've selected the equipment and the equipment's constructed for a type of environment, but you then erect it in a combustible environment, and it might be that the manufacturer does not recommend that type of environment. So you must make sure the manufacturer's instructions are fully understood and collected, and especially with new installations, they should really be stacked together and provided with the initial verification design paperwork in the operational manual. All that should be handed over to the client. We then have this 421.1.5, which again, another popular one. Not a lot of interesting information really, but it just says if equipment in a single location contains a flammable liquid in a significant quantity, so a large amount, then there'll be a need for adequate precautions to prevent any spread of this liquid, flame, and products from combustion. So if there's a quantity of liquids that's flammable stored within the equipment in use, there will be provisions to ensure that it will not spread or leak or whatever. It does say in the note that generally accepted lower limit of a significant quantity is 25. So what we're talking about is this regulation really needs consideration if we have 25 litres or more of stored flammable liquid within our electrical equipment. We then have 421.1.201, which is the popular fuse boards in the home now. Domestic, household premises, consumer units and similar switchgear assemblies shall be to BSTN 61439-3. It's common. But then their enclosure will be manufactured from a non-combustible material or be enclosed in a cabinet or enclosure constructed of a non-combustible material. And ferrous metals such as steel is deemed to be an example of non-combustible material. Again, they haven't developed this regulation any further. They've not really helped us define what is non-combustible or combustible with regards to other ferrous types of metals. They've just said steel. There's information really that's missing from this. But the whole purpose of this regulation is it's questionable. But I'm not going to go into that. I'm not going to go into any areas that's beyond this regulation's course. We know why this regulation came in, and it's still here today. I've got that's the information there. I've got the slide that kind of shows you some of the press information at the time. London Fire Brigade. This is a press release that they gave in 2014, detailing the numbers of fires where the consumer unit was recognised as a source of ignition, and you can see over time that it just got out of control, and so that's why these changes were introduced. The actual background as to why this has happened, that's not for this series. Alright, something new for the 18th, 421.1.7. So an arc fault detection device. Arc fault detection devices conforming to BSCN 62606 are recommended at the moment. Now, a lot of manufacturers are trying to obviously push this to be mandatory in parts of Europe, such as Germany. They have obviously gone that bit further, and they are becoming more mandatory in types of design in the VDE standards. But I'm not going to go into the details of arc fault detection devices in this video. I've tried to create a video on these devices. It's taken me 3 attempts so far, and I still haven't polished it because there's a lot to ask about these devices, and there's a lot that we don't know. We know the history of these devices, and we know the bad rep of their history. We know what manufacturers claim they do, but we haven't got the data to prove that. We understand what they're trying to do. We understand that they are a benefit, but there are many other ways in which these things could have been controlled. But for the sake of pushing this video series forward, I'm not going to go into any more detail. They're here. They're in the book. It's a recommendation now, so that's fine. How you decide on that is down to your risk assessment. And there is some information there, examples of where such devices can be used. Okay, include premises with a sleeping accommodation. So there's risk of arcing at night time, risk of fire. Yeah, Location with risk of fire due to the nature of process of stored material. Location with combustible constructional material. Fire propagating structures. Or locations with endangering or irreplaceable goods. So, so wherever there's a large financial or public consequence to fire, okay, wherever there is a structure that can help spread fire, and whenever there's a building that can catch fire. So, these kind of things are saying, if there's arcing that can occur, these devices will protect that. I'm not going to go into much more detail on that because I can talk. Well, the current edit's like nearly 2 hours, so we'll put a video up on these very soon once I get a bit more information from a couple of manufacturers in particular. But what I will just say, in case you've had no information on them, actually, is yes, what they do is they're considered as a device that goes beyond the current MCBs and RCDs. Current MCBs work on current and overload protection. RCDs work on imbalance of current to earth. Now, what these devices do is they obviously monitor the waveform, and they just identify distortions that conclude to be arcing events. But they work with both parallel arcs, which is obviously arc between one conductor to another within a single flex, for example, such as line to earth or line to neutral. But they'll also work with series arcs, and obviously then they're dictated by the load because you have to put a power on to actually create that. Now, series arcs are the interesting ones because a parallel arc, you get to a point where you have damaged crushed cable with a minor part of insulation in between them, you'll have a dielectric effect. And so, there may be some level of current going from one live conductor to the other, or one live conductor to earth, but due to the current level of some weak insulation, it's just arcing and it's not shorting. That arcing can build up to an excessive temperature. Okay, so there is a potential for parallel arcs, but the series one is more interesting, and this is just where you have arcing in a series connection, loose connection. It's dictated by the fault. There's no short circuit, there's no high current, and it's just a case of, how long should that fault be there. Now, in cables with these connections and these arcs, what they're saying is there's no device detecting them right now, and so these are going to stay there until either they heat to a point where they finally break due to the electromechanical stresses of that connection that then breaks it, and then the equipment stops working, and then they get that looked at. Or they just stay there idling to the point where the temperature, they're still maintaining integrity for current to flow, but the temperature is collected to such a high level that they start to catch fire. So I'll add a lot more content on them and how they work in another video soon. 422. Precautions where particular risks of fire exist. So this is where, due to some scenario with regards to the environment or the type or the use of the installation, there's a risk of fire. So again, a good clue with this is if there's a question in this section, it'll probably start with the words where a particular risk of fire exists. Okay, this is what we're talking about now. Protection against where fire may start due to some circumstance, such as we have an issue with fire and evacuation is a problem. Or we have an issue with fire because we're storing combustible material. We have an issue with fire because our building is made of combustible material. We have an issue with fire because our building will allow fire to spread exponentially. We have an issue with fire because if this place catches fire, then either huge amounts of money are lost, huge amounts of industry is disrupted, or irreplaceable goods are obviously damaged. A good example of this one would have been the old Windsor Castle fire, that kind of thing, the amount of money to kind of repair after that. That was in the early 90s, I think. So, these kind of things need to be looked at, and we need to select wiring systems, and we need to make sure we identify where these risks can occur. So we start with 4221. We'll go to 422.2, which just gives us a couple of external influence categories with regards to the conditions for evacuation in emergency. So it just says if our installations of low density occupation with difficult conditions of evacuation, then it's a BD2. So that could be difficult condition of evacuation. So maybe a hospital, so not an excessively populated area, but moving people out could be a difficult operation. You then have high density occupation with easy condition of evacuation, BD3. So this could be a cinema, a lot of people in a small area, but the ease of getting out due to the dedicated escape route. Could be a stadium, A lot of people in an area, but the ease of getting out onto the centre of the pitch, etc. So a lot of people in a smaller area, but an easy way to get out. Then you have BD4, high density occupation, difficult conditions of evacuation. This obviously is the worst case, such as the tower blocks illustrated here, where there's lots of people, but they have very small paths to exit if they need to exit in an emergency. So there's, identifying these different categories, and then there's obviously requirements with regards to wiring systems and cable types for ensuring that they remain operational in a fire condition, and they do not assist with the spread of fire, inhibit the spread of fire. Alright. 4223. Location with the risk of fire due to the nature of processed or stored material. So, illustration here is obviously a wood workshop, but any kind of site, a paper mill, paper silo, even some flour silos, some in the food industry, anything where you're storing material or you're making product and it's combustible. Okay, you need to identify that many different things are combustible. It's not just things that you typically would expect to go up. Many things are combustible, and there must be obviously assessments for those risks. One of the things that we have here in 422.3.1 is a consideration on a luminaire from a combustible surface. Now this actual regulation repeats itself, 422.3.1, but if you actually then turn the page, you also have it in 422.4.2. And the information is the same. It's all about a luminaire being kept at adequate distance from the combustible material. But with 422.3.1, this is where we're storing a combustible material. And in 422.4.2, this is where our building is made of combustible material. So, technically, the proximity, doesn't change. It's just that the thing that can catch fire, once was material, and in the other one is actually the building itself. Okay, so we have rating up to 100 watts, half a meter, between 100 and 300, 0.8 meter, and over 3 up to 500 is 1. Now, this obviously is thinking about the times when all of our luminaires had, or most of our luminaires were of incandescence, so we'd obviously use heat to create light, and so boundaries were an issue. Also the halogen dichroics. I nearly set fire to a pub once. Wasn't my fault. All right, but yeah, I was rewiring a pub, and I put some lights in the toilet, and the doors swung out, and it was just a 50 watts. Didn't heat the head up too much when you sat on the throne. It was absolutely fine. It was far enough. And then just as I was doing initial verification a few weeks later, I was sat at the bar, testing the taps that had just been connected up, and the carpenter had been back on site, and I could hear his radio and I could see all his tools everywhere. I was just doing all the certs. I didn't think about what he was doing, but he went off on the phone out in the car park, and I noticed a smell of burning. And what he was actually doing is he was changing the doors from swinging out of the cubicles to swinging into the cubicles. And the way he was doing it with the springs at the time, their natural rest position was right under the light. So it was about that far. And what was happening is the heat from the light was actually basically just burning a hole into the top of the door. So, whilst technically not my fault because I assessed this light proximity and heat at the time, but there was no door there because it went the other way, I took action to fix it. And this is back when you could get GU10 LEDs, and they were probably like 12 quid at the time. So we're talking about a number of years ago now. But that created was a whiter light at the time, which the client wasn't very happy with. But the heat was just a lot. The thermal effect wasn't as bad at all. So you do need to understand that, this is specific for luminaires. This probably will be updated in time as we change our, we're regularly changing our luminaires these days, but we need to consider any hotspots that occur. We also say 422.3.2 that measures will be taken to prevent an enclosure or equipment such as a heater or resistor from exceeding the following. So 90 degree under normal condition and 115 degree under a fault condition. What we need to identify, if we're in a location with where we've got processed or stored materials that are conductive, we've got to identify that a lot of electrical equipment will use methods such as convection cooling, where it'll have little fans that will push that temperature out, push that warm air out, so bring the cold in, push the warm air out, and that will build up high levels of heat build up just around the edges of the enclosure. And if there are combustible materials that can fall onto this equipment, we've got to identify limiting temperatures. Now this is obviously, it's just going to be, again, it's like a guidance, because this is the regulations as guidance. So make sure the manufacturer identifies any potential combustible parts making contact with it, and it probably will have some kind of disclaimer that says that there should be a limit or a boundary, or equipment just should not make contact with it. If it has to, though, you can obviously upgrade this kind of equipment. This kind of equipment just uses convection, but you can use things like forced cooling, which is where you bring in the cold air and you push out the hot in one direction. A bit like my PC, where I bring the cold air in and I go pushing the hot out the top. So I can direct that. I can direct the passage of the warmer air out. Or you can then have a closed loop system, a bit like a water cooled system, where it brings the cool in and it just circulates it around over a heat sink. There are many methods to keep temperatures down, but we need to identify these risks and make sure we select equipment that will not create a large temperature, or a temperature around these numbers, around stored combustible materials. Okay, so 4223 and 4224 are fairly similar. One is materials, one is structure, but combustible, the rules are the same. There is a mention in 42239 of the need to have an RCD with regards to fire protection. There's a mention of that there. We're going to mention that again later on with protection devices against thermal effects in part 5, but it gives you a little preview of it here. It does say that if we're going to have an TT or a TN system, the RCD will not exceed 300 milliamp. Okay, we're going to see this later on in part 5. The general rule is with fire protection for RCDs, no more than 300 milliamp, and it should be installed at the origin of the installation. Okay, those are the general rules. But if we have a resistant fault, then we need a 30 milliamp RCD. That's mentioned there as well. Nothing else that's really worth mentioning in 422. There's a mention with luminaires and equipment. It says it'll be appropriate for the location. That makes sense. But, selection and erection is very important. Provide with an enclosure for a degree of at least IP4X, or if there's dust present, IP5X, and if there's electrically conductive dust, IP6X. This is obviously the dust height IP ratings. Okay, we'll refer to those as we get to chapter 52, where we look at external influences again. But your understanding on IP codes shouldn't be much of a problem, because we're going to use them a lot, especially in part 7. Alright, so there's requirements there. Allow a limited surface temperature, and will be of a type that prevents the lamp components from falling from the luminaire. So there'll be like a containment, there'll be a lid or something that contains all the equipment. No control gear will fall out of the luminaire, because obviously, you have a combustible location, you have equipment that can fall out that's of a high temperature. Again, remember, ballasts and chokes and old luminaires get to really, really hot temperatures, and if they were to fall out and land on combustible material, they'll go up. To finish off then, let's look at 423, and again, a little clue there that this may be mentioned. This is just a little bit on protection against burns. So when we actually do install equipment, whether it be a wiring system or, more importantly, current using equipment, could be something like a hand dryer or a controller or a switch or an isolator, we need to recognise that there's a limiting temperature. There's a limiting temperature to ensure that we don't get burns. We have to protect from burns. So the questions are, well, first, is it metallic or non-metallic? Because if it's metallic, it will obviously it'll be warmer to the touch due to the way thermal energy works through metals, leaving metals and as we touch them. But also we need to say, right, does this equipment require us to actually touch it? Or does it require us to sometimes hold it? Or does it require us to hold it at all times? Because depending on how that works and how the equipment needs to be used, will also depend on what temperatures it can reach. So the general rule is, if it's metallic, it has a lower maximum temperature, because it's easier for the energy to to escape it and come as you come in contact with your skin. So metallics have lower limits, but also the equipment, if you have to hold it, has a lower limit. So if you look at the table there, table 421, if I have to hold the equipment to use it, the accessible part has to be in my hand, and if it's metallic, it has to be no more than 55 degrees C. If I don't need to touch it at all, and it's non-metallic, it can actually go as far up as 90 degrees. Okay, and then you have the scenarios in between that you can see from this. So do make sure that you understand that there is a need to protect against burns as well. All right, so that actually closes 42, and this is half an hour. Okay, so we'll do another video for chapter 43. We'll close chapter 42 now, but do remember that we must recognize energy that can be given off by equipment. Radiant energy, running thermal patterns, hot spots. We need to recognize that we need to protect against the burn from handling the equipment. We need to recognize that if the equipment arcs or gives off sparks while it runs, it needs to be screened. We need to recognize that if there's a requirement to store liquid that's flammable, we must recognize that there's a value of 25 litres or more is a significant thing that needs extra measures to be taken. We also need to remember that the metal fuse boards in the home have to contain fire, because apparently now we like setting fire to fuse boards. And we also have the arc fault detection device, which right now is a recommended device. We'll talk a bit more about them as well in part 5 as we come to them. But we'll finish this video off now. Nice to finish off on the half hour. And I will get things ready, and I'll start doing the next video, which will be chapter 43, protection against overcurrent. See you then.